Ocean acidification is caused by an increase in atmospheric carbon dioxide. Our oceans absorb this carbon dioxide, and this leads to a reduction in the availability of carbonate ions, which are crucial for shell calcification. Calcifying organisms require calcium carbonate in order to build up their shells or exoskeletons. And previous studies have shown that elevated carbon dioxide levels result in weaker shells and an overall lower survival rate for base scallops. Although they may seem insignificant, Argopecten irradians are actually a keystone species in many coastal ecosystems because they're filter feeders. They're also critical for aquaculture and fisheries, especially those on Long Island. Given their importance, understanding how these environmental stressors, like ocean acidification and changes in temperature, impact base scallops is vital for protecting them. My study investigated how different water temperatures of 16, 18, and 20 degrees Celsius waters and how ocean acidification affected the structural and chemical properties of base scallop shells. I hypothesized that warmer waters will increase the shell smoothness and width, but weaken the overall structural integrity due to a reduction in calcification caused by ocean acidification. Before my scallops were placed under experimental conditions, they were born in a hatchery on Long Island and then transferred to the shorelines of Orient Harbor, where they were left to grow for about 2 years. Afterwards, they were placed under experimental conditions for about a year and a half. My experimental conditions consisted of 3 groups. I had hot group, which had 20 degrees Celsius water, the ambient group, which mimicked normal water temperatures of 18 degrees Celsius, and my cold group, which had waters of 16 degrees Celsius. And I analyzed the shell morphology and elemental conditions for all of these, while the ambient seawater temperature served as a control. These experiments allowed me to isolate the impacts of temperature and acidification on scallop shells in order to further analyze them. In my experiment, I used 4 key methods to assess the impacts of ocean acidification on shell morphology and composition. The first one being scanning electron microscopy and energy dispersion spectroscopy. The scanning electron microscope is an extremely powerful microscope that shoots a beam of electron onto a sample in order to produce an extremely clear picture of a sample. And I use the Hitachi S4800 SEM with a magnification of 40 in order to get these extremely detailed pictures. I use the ESX-4010 detector onto the Hitachi microscope in order to focus on calcium, oxygen, and trace elements at the specific spots. In my experiment, I analyzed the bottom, the middle, and the top part of the shell for each of the SEM, EDS, and XRD scans. My second method was X-ray diffraction. I just used the Recruit Smart Lab XRD scanner in order to identify crystallological changes due to environmental conditions. My third analytical technique is a micro-CT scanner. I use the SkyScan 1173 scanner at 80 kilovolts in order to capture 3D structural data to analyze shell thinning and weakening. In order to process my micro-CT data, I use the 3D Slicer software to quantify morphological changes. It was observed with the SEM data that those shells grown in the hot group experienced smoother texture and faster but more uneven growth, and had prominent cracks and porosity near the growth edges, while those in the cold group experienced a rougher texture, slower growth, but they had well-defined ridges. And the ambient group demonstrated that there was a moderate growth with a smoother middle section and a steady structure. These studies demonstrate that the elevated temperatures negatively affect shell structure and integrity, and that the warmer water may promote growth, but it weakens the overall structural integrity, while the colder water slows growth and increases the roughness. In my EDS analysis, it showed that there was higher magnesium and iron concentrations in elevated temperature conditions. Magnesium levels increased by 250%, from 2% in the ambient to 7% in the hot group. And the iron levels increased by 500%, from 0.5% in the control to 3% in the hot group. As you can see in this graph right here represents the control, this represents the hot, and this represents the cold group. As you can see, there's a greater abundance of trace elements present in the hot than that in the control. Cold water shells showed that there was a balance between the elemental conditions, including iron, cadmium, and other elements, and these elemental shifts suggest that thermal stress influences the shell composition, which is possibly linked to metabolic changes. For statistical analysis, one of them being the ANOVA test, it showed that there were significant differences between the peak group groups, and that the calcium for 63A, aka the hot shell, was significantly lower than those in the cold and damp group, and the magnesium levels were also significantly lower compared to the other two groups. For my HSD threshold matrix, positive values confirm differences between temperature groups, while my values were negative. It concluded that there is no differences between temperature. Although both groups contained aragonite as a primary phase, the hot group had a reduction in their aragonite crystallinity. There were minor calcite peaks that were detected in elevated composition, suggesting that there is a shift in mineral composition, with there being major peaks that indicate calcite with trace iron. Although the control group had a uniform, smoother crystal arrangement, the elevated temperature had irregular aragonite patterns, which increases the defects and fractures of the overall shell, and therefore the heat stress disrupted the crystalline structure, leading to weaker shells. From my micro-CT images, it can be observed that the hot group had wider ridges and rapid growth with weaker integrity, shown right here. Cold group had tighter ridges with a slower and stable growth, while the ambient group experienced a balanced growth and more structure. It was concluded that elevated temperature resulted in thinner shells, and that these 3D reconstructions revealed weaker overall shell structure in areas with high porosity or growing around the shell's edges. Elevated temperatures and ocean acidification weaken scallop shells by increasing the elemental imbalances, disrupting crystal growth, and inducing cracks and porosity. Cooler temperatures promote better shell integrity, but the growth is much slower, and these findings highlight the potential long-term risk of climate change for scallop populations and coastal ecosystems. Understanding these impacts help protect scallops and maintain sustainable fisheries. As a result of my future works, I want to explore how scallops can adapt to long-term ocean acidification and warming. And I thank you for your time and consideration.